Welcome everybody. So we have already solved quite a while ago the infinite square well, and now that we are learning, quantum mechanics in more dimensions, let's take a look at something that is the infinite cubical well, also called the particle in a box. Now, what this is basically the same problem, right? Let's just draw the situation here. So if we have a three-dimensional system, let's say z is over here, x is over there, y is somewhere over there. Let's make sure x, y, no, they have to be the other way around in order for this to be correct. So this has to be y and x, even though it doesn't really matter. And this is just to sketch the situation. So we have a box, right? This is 0, this is a in x, and somewhere over here is a in z. So, you have a box, maybe like that. It goes down. Not the best drawing of a box. I'm not good at drawing. But you get the overall point, right? So you have this box in 3 dimensions. Of course, I drew something that is not really boxy. But the point is that there's an infinite potential everywhere outside of this box. So your particle can only exist inside, right? The wave function will only be non-zero inside of this box. Okay, so that's the point. And there is basically 3 square wells, but just one in every direction, right? You have one in the y direction, one in the x direction, and you're going to have one in the z direction, right? And well, we will see that explicitly. So part A asks us to find these stationary state wave functions and the corresponding energies. So how do we find wave functions? Well, we solve the Schrodinger equation, and well, that's how we get them. So let's write down the 3-dimensional Schrodinger equation. And keep in mind that our wave function can depend on x, y, and z. Of course, we don't know what it is yet, but keep in mind that that is something that could happen. Now, we say plus, and then we have our potential. Now, our potential, what is it? It is 0 outside of the box, inside the box, and infinite outside. So what this means is that there can be no wave function outside because the potential is infinite, and we have already seen in the first few chapters here on the course that we cannot have a wave function under those circumstances. So the only region where there is a wave function is the region where the potential is 0. So, well, goodbye potential. All right, so then we have this is equal to the energy times the wave function that depends on x, y, and z. Okay, so now what we are going to do is we are going to look for separable solutions, right? Just like we will do in the case for the hydrogen atom, for example. So what we will do is say, okay, let's look for solutions that are of the following form, that are of some function that depends only on x times some function that depends only on y times some function that depends only on z. So we are assuming that it exists. If we end up not being able to find anything, then that means, well, that this didn't exist, and then solving this would be much, much harder. But let's be optimistic here, and let's say, okay, hopefully that exists. So we can now rewrite this as minus h bar squared to m. Then we are going to have, let's for now keep the operator there quite in general. And we're going to have x, y, z. So x that depends on x, y that depends on y. Now keep in mind, this big X is the function, small x is the variable. This can be a little bit confusing, but that's why we're using parentheses so that we can keep track. And E times x of x, y of y, z of z. Okay. Now, what next? Well, keep in mind that since we are going to be solving this in Cartesian coordinates, I mean, look at the symmetry of the problem, right? Why would you use any other system? Then our operator here will simply be the x derivative twice, the y derivative twice, and the z derivative twice. All right, so we just multiply now, and we get the following. So let's begin by just dividing by this so that it ends up on the right-hand side. So on the left-hand side, we get second derivative with respect to x of x, okay, let's put a parenthesis here, x of x, y of y, z of z. And then we have plus, then we have the second derivative, but now with respect to y of x, y of y, z of z. Then we have plus the second derivative with respect to z. And then we this is of x, y of y. Let me zoom out. Z of z. And on the right-hand side, we get minus 2me divided by h bar squared, and also xyz. So now I'm going to be a bit lazy and say xyz. Okay, because I think it's clear what those xyz's are. So now what we do is a very standard procedure for this sort of problem. We divide by the functions x, y, z. Okay, so when we do that, let's see. Notice first that here, y and z, the functions, do not depend on the coordinate x. So for that reason, we can take them outside. So we get y times z, right? These are the functions. I'm just not writing the coordinate dependence explicitly, but it's just to save time. So this is what we get, y times z, plus, now we pull out x and z, so we get x, z. By the way, I haven't divided yet, so this is 1 over x, y, z. I'm just doing this step by step. xz d squared y dy squared. This is a function. This is not the coordinate. That's why this derivative is not 1. Then we have plus d squared dz squared of z. And in front, we need to put x and y. And this is equal to minus 2me over h bar squared. Okay, what next? Well, now just multiply through here. So this would be 1 over xyz gives us 1 over x here. So this is 1 over x, the function. Here we have 1 over y. And here we have 1 over z. Okay, and this is going to be our differential equation. Now we can just go maybe a little bit further, perhaps, and just put the minus sign on the other side, even though it doesn't really matter all that much. You can put it wherever you want. And we can rewrite this as 2me divided by h bar squared. This is, now take a look at this. This is going to be kx squared plus ky squared plus kz squared. So I simply called this with the minus sign kx. This here with a minus sign will be ky. This here with a minus sign will be kz squared. Okay, all of them squared, of course. And this is just to make sure that we get our typical way of writing the energy, as in the energy is h squared over 2m, right? If you look at this, the energy would be h bar squared over 2m times kx squared plus ky squared plus kz squared, which really should remind you of what we had for the infinite sphere, not spherical, sorry, for just the infinite square. Well, the spherical will come later. Okay, so now just take a look at each one of these equalities here. So we said kx squared is equal to minus d squared x, that being the function, of course. And then we have dx squared and 1 over the function x. Okay, and notice, of course, that each one of these is exactly the same. So ky and kz have exactly the same form, but you just replace x for y or for z. So we will only solve it once because the other ones are exactly the same, but in other directions. Okay, so how do we solve this differential equation? Well, just use whatever form you like most. I will show you mine. Now, what I like to do is just write everything on one side. Let's have this be positive. So let's write this as d squared x dx squared plus kx squared times x, right? So I multiplied by x. that has to be equal to 0. Now here I will factor the following way. So I will say, first of all, I factor out the x to the right, so I get d squared dx squared plus kx squared, and this is times x. And now I will do something quite interesting. I will write this as minus I squared, right? Because I squared is minus 1. And why do I do this? This is actually the same that we did in the case for the infinite square well. This is the way that I like to solve this, because now I can write that parentheses as d over dx plus I kx times d dx minus I kx, right? It's completely equivalent. Assuming, of course, that kx commutes with the derivative operator, which it does, so no worries there. Okay, so now in order for this to be 0, either this times this is 0 or this times this is 0. So each one of those will give us one of our solutions. So let's go for the first one. So the first one would be d dx plus I kx. Now, both of them are acting on x. This is equal to 0, which means, of course, that dx is going dx is going to be minus I kx times the x function. And now we separate the variables, so we get dx over x is equal to minus I kx dx. So we integrate both sides. Here we have the natural log of x. This is equal to minus I kx times x, the variable, not the function. This here is the function on the left-hand side, so this is function, and this is the variable. So it's a little bit confusing, but just pay attention to what everything is. And of course, plus some constant of integration. Now, let's exponentiate everything, and we get that x, the function, right, x that depends on x, is going to be e to the minus I kx times x times e to the c. But e to the c is simply some constant, so let's just call this a. That's just some random constant. Now, we do the same, but for the other situation, this one right there. So here we have dx times x, and let's just write it on the other side right away. So we get plus I kx times x. So we separate variables, so we get dx over x. It's going to be the same thing, only a minus sign is changed. So we get I kx dx. We integrate, we get a natural log of the function x is equal to I kxx. We exponentiate, and we get that x as a function of x is equal, plus some constant, of course. There's going to be some other constant, e to the I kxx. So our solution here, our complete solution will be a linear combination of both of those solutions. So we get a e to the minus I kx times x plus b e to the I kx times x. So this is correct, and you could use this, but we are dealing with basically spherical square wells. Sorry, I don't know why I keep saying spherical. We're dealing with square wells. So we know that right, we separated it into three different ones, so we basically split it into three square wells. So it is much more convenient to use cosine and sine form. Now, I have made an entire video about this, but I will just quickly show you, right? We can just go using Euler's formula from this notation to cosines and sines, and it's perfectly acceptable. So we know that e to the minus I kx times x is cosine of kx times x, and then plus I sine of kx times x, and because there's a minus sign, we can put the minus sign in front, right? The sine is an odd function, so we can just pull it outside, right? This is because sine of minus kx times x is equal to minus sine of kx times x. That's what I just used there. Okay, then we have b times cosine of kx times x plus I sine of kx times x. Okay, now we factor everything with common terms, so we get cosine of kxx, factor of a plus b, and then we have plus sine of kxx, factor of, let's see, well, we can now put the I in front, so let's put it just here, I times minus 1 times a plus ib. So notice that if a and b are any numbers, real or complex, then this is simply any other number, right? I don't know, a tilde if you want. And this here is any other number, just b tilde. So in the end, this is simply a tilde cosine of kx times x plus b tilde sine of kx times x. And a and b, a tilde and b tilde, they're just names. We can just rename this as a and b and just forget about the tilde. So this is our function x of x. Now, in exactly the same way, doing exactly the same, we get that y of x, sorry, y of y, sorry. This is a. Now notice, okay, we're going to have a lot of constants, so let's call this ax, bx, and let's just call this ay, right? Cosine of ky times y plus by sine of ky times y. So literally the same, but every x is a y, and now we go for z, which gives us z of z, which is a z, cosine of kz times z, plus bz, sine of kz times z. Okay, so these are our three, each one of the wave or the kind of partial wave functions, right? Because we know that psi itself is going to be the product of those. However, before we use psi is equal to x, y, z, we have to apply boundary conditions. Okay, so let's now apply boundary conditions. So let's do it for the case of x. So let's apply boundary conditions. So what are our boundary conditions? Well, we want our function x to be 0. Right? Our function x has to be 0 at 0 and at a, right? At both ends of the box. Okay, so that's our condition. So let's plug it in. So we want that ax cosine of 0 plus bx sine of 0 have to be equal to 0. So this means cosine of 0 is 1 and sine of 0 is 0. So this is 1, this is 0. So we get that ax has to be equal to 0. Right? So that's our first condition. So that is when we use x0 equal to 0. So that's what we get. Now let's use xa equal to 0. So let's use that now. So we know now that ax is 0, so we get bx sine of kx times a, which is going to be 0. And for this to be 0, we need that kx times a has to be some integer times pi, right? 0, 1, 2, 3, 4, I don't care. But since we have x, y, z, let's call this nx, because we have to do the exact same procedure now for the other ones. So this means that kx is going to be nx pi over a. Okay, where nx is 0, 1, 2, 3, blah, 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 blah. I guess we usually start at 1, right? Because the 0th state, well, you're going to get 0, so I guess it doesn't make much sense. But well, in principle, you could consider it. Now, since the other equations are exactly the same, we get exactly the same results. So we get ky is equal to ny pi over a, and kz is equal to nz pi over z. All of them have the same conditions, right? 1, 2, 3, 4, 5, 5 is what the y and z are. Okay, so given that, you can now go ahead and rewrite the wave functions that we found here. So x of x, we now know ax is 0, so bx, here we have bx times sine of kx, which is nx pi over a. And let's not forget about x. There we go. Okay, so now y of y. This is the same thing, of course, right? They are all exactly the same. There's no difference in which spatial direction you're using. So as we saw, they are all exactly the same. That's why we only solved for one. So notice that it is the exact same procedure that we had done for the infinite square well, but now we just do it 3 times. We haven't normalized any of this though, so let's do that. Now choose any of them. Again, they will all be normalized exactly the same, and to be honest, we already did this, but I will show you this just, to be thorough. So 1 is equal to the integral from 0 to a of bx squared sine squared of nx pi over ax dx. And now I'll just choose whichever way you like the most. Now, what I like to do is say, all right, we know that sine squared of, theta plus cosine squared of theta is equal to 1. And we also know that cosine squared of theta minus sine squared of theta is equal to, that would be cosine of 2 theta. So using these together, right, we can, in this case, we want sine, so we can subtract them. So this equation minus that other equation. So we get sine 2 times sine squared of theta. The cosines cancel out. 1 minus cosine of 2 theta. And this we just divide by 2. There we go. So this is the way to rewrite sine squared. And that way we get rid of this squared, because that was kind of hindering our attempt to integrate this. Right? Now we can write this as integral from 0 to a bx squared, and then 1 minus cosine of 2 theta divided by 2. And theta, of course, in this case, is going to be nx pi over ax dx. Okay, so that's how we do that. Now we just integrate, right? We have 2 different parts. The first one is going to be bx squared integral from 0 to a of just dx divided by 2. So yeah, this is not particularly difficult. We do that, we get x over 2. We get x over 2 evaluated between 0 and a. So that is simply a over 2, right? So that's all we get, a over 2. Then we have minus 1/2 the integral from 0 to a of cosine of, I think I wrote 2 times. So cosine of this thing right there. Now the integral of cosine is sine. So actually we can just write it immediately. So that is sine of 2nx pi over ax. And this you have to now multiply. We're integrating, so we have to multiply by the inverse of what is inside, 2nx pi. And we evaluate between 0 and pi. So at between 0 and a. So at a, this thing gives us 2n pi. And pi is an integer, so this is always 0. And at 0, it's also 0. So it turns out that this part is always 0. So goodbye. So what we have in the end is this, right? Which means that bx, or bx squared, now let's just say bx, this is going to be square root of 2 over a, which is of course exactly what we had in the case for the infinite square well. I mean, we didn't expect any different. And it's going to be the same for by and bz. So with this, finally, we can write the wave function for the infinite cubical well. So this would be, it is 2 over a, right? Yes, 2 over a. So this is 2 over a square root cubed times sine of nx pi over a times x times the sine of ny pi over a times y times the sine of ny pi z a. All right, so this is what we wanted. That's the wave function, okay? So we still need to figure out what the energies are. And just notice that the wave function in the end, it is nothing but just multiplying 3 different wave functions of an infinite square well, but in different directions together. That's what it is. Now, what about the energies? Well, we already found the expression for the energy quite a while ago here. Right? All we need to do is just plug in our values for kx, ky, and kz, right? Because we know that kx has to be nx pi over a. All right, so we do this. And here we have that the energy is equal to h bar squared over 2m. And now we have nx squared pi squared over a squared plus ny squared pi squared a squared plus nz squared pi squared a squared. Okay, and here we can simply factor out some things. So we get that the energy is h bar squared pi squared 2m a squared. So this part is exactly the same as in the case for the just regular square well. And then we have nx squared plus ny squared plus nz squared. So this is the energy. Right, so there we go. We found the wave functions and the energy. And now we will take a closer look at the energy with part B, because this is actually very interesting. It's one of the first times that we encounter degenerate states. So notice this, right? Let's call the distinct energies E1, E2, E3 in order of increasing energy, right? We can have a different combination of states. Before we had, E2 is simply the second state, but now we can have a lot of combinations, right? So we can have maybe in X direction, you are in the ground state, but in the Y direction, you are in the second or third state, right? And in the Z direction, maybe you are in the ground state or in the second state or in the first excited state or in the second excited state. I don't know, right? You have a lot of combinations. And many of them may have very well the same energies. So now we want to find the 6 first ones, right? So find E1, E2, E3, E4, E5, and also determine the degeneracy of each one, which means the number of different states that share the same energy, okay? So let's do this. Okay, so let's just begin with a little bit of a table. So nx, ny, and z, and then the sum. So let's just write it like this, the sum of those values. Okay, so, and why do we care about the sum of those values? Or rather, the sum of, I'm gonna write like this, from 1 to 3, 1 being x, 2 being y, 3 being z, squared. Right, and we care because that's what we plug in here, right? Okay, so this would be, the first possibility is 1, 1, 1. This is the ground state. So in that case, the sum is 3. And what is the degeneracy? There is only, well, one combination that gives us 3, right? There will be no other value for the energy, right? Because the energy is just these constants times this number. So there will be no other value for the energy that can have this same, or no other state that can have the same energy. So there is degeneracy 1. It is not degenerate. Now let's go for 1, 2, 1. Let's maybe make a separating line. So this, when we sum the squares, we get 1 squared, 4, 1. So we get 6. We can also have 2, 1, 1 or 1, 1, 2. All 3 of these states have the exact same, maybe let me erase this. I don't like having it here. All of those states have the exact same energy. But all of them add up to 6 times the constants. So this is 3 times degenerate. It is threefold degenerate. Now we can also go, for example, for 1, 1, 3 or 3, 1, 1, or also you can go for 1, 3, 1. All of these have a total of 11, right? This is 11, 11, and 11. All of those have a total of 11 times the constant. So this is also threefold degenerate. right? And we can call this, by the way, this would be our E1. This is going to be our E2. This is going to be our E3, right? And here, what do I mean by this? This is going to be simply pi squared h bar squared over 2m a squared. And then this is that same thing times 3. Times 6. This is times 3. This is times 6. And this is pi squared h bar squared 2m a squared times 11, and so on, right? So let's now go for E4, right? What is the next energy state? Let me get rid of these things, blah, blah, blah. All right. So next, well, what is the next? If we were to go for 1, 2, 3, for example, in this case, this would be 9 plus 4 plus 1. So this would be 13, 14. But there is another state that has fewer energy. If we take 2, 2, 2, right? So this is simply going to be 4, 4, 4. So this has 12, right? It is not degenerate. There's only one combination here. So this means that E4 is going to be 12 times all of our constants, right? Those. Then we have 1, 2, 3, 1, 3, 2. Then we also have 3, 1, 2. We can also have, wait, let me get rid of, okay. We are running into our previous calculations. Goodbye to all of you. Any second now, there we go, okay. So this is 3, 1, 2. We can also have, I don't know, 2, 1, 3. We can also have something like 2, 3, 1. And I think that's all the possible combinations, right? We had 1 and switched 3. Oh no, I'm missing 1 with 3. Okay, so I'm missing 1 with 3. So we can also have 3, 2, 1. So in all of these cases, we have a total of 14, but this time we have 6 different ones. So E5 is going to be 14 times this thing. Now there is one state that I think I forgot before, but we can just relabel everything. So we can also have, for example, 1, 2, 2, 2, 1, 2, and also 2, 2, 1. In that case, this is a 4, 4, 1, so that's 9, and we have 3 of them. So this is 9, so this should actually be further up. So let's just do a little bit of renaming, even though it doesn't really matter, but this is E4, E5, E6. So this is E4, E5, E6. And the E3 is the one that we just found. So this is E3, which is 9 times, our beautiful constants. So there we go. We found the different energy states. You can see that each one of your states can have different values. They can be in excited states, in the ground state, and they can have all sort of combinations. And now, of course, finding which state has more energy than the other is not all that trivial, right? Sometimes you can just get it confused. But it's also important that now several energy states can give you the same, or several combination of states will give you the same energy, which means they are degenerate. Okay, so that's very important. Degeneracy will be quite an issue going forward. All right, now they ask us, what is the degeneracy of E14 and why is this case interesting? E14, let's just go through E7, E8, 9, 10, 11, 12, 13, and then we go for E14. So E7 would be the next one after 1, 2, 3. So after 1, 2, 3, of course, comes 2, 2, 3, right? That makes the most sense. So this gives us a sum of nx squared plus ny squared plus nz squared of, let's see, this is 2, 4, 4, and 9, so that's 13, 17. So this would be 17. Then after this, let's see, we could either go for 3, 3, 1. So 3, 3, 1 would be 9, 9, 1. So that's 18, 19. Or we could perhaps go for 4, 1, 1, which would be 16, 17, 18. Okay, so it's actually 4, 1, 1 next. So first we go for 4, 1, 1. So E8 is 4, 1, 1, which gives us 18. Then we have E9, which is 3, 3, 1, and all of its combinations, which give us 19, right? So 991, yes. Then we could go either for 332 or 412 or 421. So 421 would be, that's 16, 20, 21. And the other possibility of the next one would be 332, but that would be, that's 18, and 4, that's 22. So that comes later. So then we have E10, E11, so we are getting closer. Now the next possibility would be 422, right? 422. So this would be, that's 16, 20, 24. Then we have E13. Let's see, here we could go for, I guess, 431, right? So that's 16 plus 9, that's 25, 26. Okay. And now finally we can get at E14. So E14, this would be 333, which gives us 27. But there's actually another possibility, right? Because we can also go for 511, right? This also gives us 27. So what is the degeneracy of this? It would be, well, there's one combination, 333, and there are three combinations here, right? 115, 151, 511, right? So in total we have 4 combinations. And now, why is this case interesting? Well, it's simply interesting because we have to keep in mind that there can be additional possibilities in terms of which states give us the same result. Right? It's not just 511, 431. Sometimes you're going to get these sort of coincidences where, because you are squaring numbers, there are going to be even states that don't really have much in common, like 333 and 511, that give you the same energy. So in degenerate states, sometimes it's going to be a little bit harder to find all the energy states, especially if you have to calculate them by hand. But yeah, keep in mind, degenerate states usually do mean that things are a little bit more complicated than usual, but it's still manageable. So this was the problem. I hope that this video was useful to you. If it was, please make sure to leave a like on the video, comment and subscribe, and maybe even consider checking out my Patreon. So I'll see you in the next video. Thank you very much for watching.